And we'll start from current slide. Okay. That's not the one I wanted, but we'll go there. All right. The question I had for you, did any of you... All right. Name, please. Yeah, Kayla. All right. Okay, 6. Enough for a volleyball team now. Okay. Just a question. Did any of you come Thursday? Last Thursday? Okay, all of you knew we weren't having class. Now, here's what I was told. I don't know if this is true or not. That the power went off here. Because one of the instructors from West Campus came over to give me something. And she said, I couldn't find you. There was no power and the building was empty. So, but I don't know what time she came. I'm guessing it was probably after 5:30, so I don't know. That's why I was wondering if any of you came. Because I know at our home in Birmingham, my wife said they lost power mid-afternoon, and it was off when we left because we hit the road. It was probably 5:30 or 6 before we hit the road. So it was off for several hours there. And I just wondered if it was that situation here, how we lucked out by having the class and not having to miss class. So that worked out nicely. Sorry, I felt bad that I was asking y'all to do that, but then when I found out the power was off, I thought, well, maybe this turned out to be a good thing after all. Okay, that's... trying to find you now. Tiffany, right? Okay. Anyone else come in, Sister Caldwell? Okay. Okay. Any questions on anything we've done so far? As I was saying before, a couple of you came in. I have a few people who haven't turned in test 1 and test 2. And then all of you have test 3, I hope, out now. You don't have test 3? Okay. Let me see if I can find it. There's test 1. Test 1, test 2. And that's still test 2. Here's test 3. Okay, and hold on, don't go anywhere until I explain an error on it. Anyway, okay, yeah, let me explain an error that's on the test. Okay, Caleb. Okay, number 3. Now yours has something marked there, but I want you to understand what it is. The vertical steel columns of an office building each support a weight of, I've never seen a number like that, 50,00. They missed the 0. I don't know how they did, but that's 50,000 pounds. Okay, and then part B, what would the compression of the weight be if it was, and they did the same thing, 60,00, leaving off the third 0, that's 60,000 pounds. Okay, does that make sense? Okay, and this is Stasi, right? All right, good deal. All right, now, I was just going through and saying I still am missing test 1 and 2 from a few students, not many, but a few. All of you, I think, have test 3 still out, so, and I just gave it to the last 2 people. And last time, I'm pretty sure a few of you elected to go on and take test 4, but we haven't quite finished it. Did some of you take it then, or not? Oh, you didn't? Okay. Well, I think we'll be ready to take it today, when we leave. Okay. Any other questions? Any questions at all? All right. We're on chapter 16, which I would think for folks getting into sonography, sound waves would be probably one of the more important issues chapters that we cover. We covered 16.1 and 16.2. We're now going to 16.3. I don't think we got started on this last time. Okay, I didn't have it marked anywhere. So let's go from here. All right. Now, sound basically is an energy. It's caused by a compressional wave. We've been talking about that. And it says here, and I think most of you have books, so I won't read all of it, but I wanted to put this out there. There has to be a source of sound, okay? That's a medium. Okay, a source of sound, that's the thing that produces the sound. Like right now, it's my voice, okay? I'm producing the sound. If you can hear sound from somewhere else, then that may be a source, okay? So you got to have that source of sound. The medium, if we were in outer space, you would not hear a word I said. Because, well, number one, we'd be in big suits and stuff, but there is no air. There's no medium to conduct the sound. Like I said, sound is a compression wave, so there's got to be something to compress. There's got to be, okay? So you have to have a medium. Most of the time it's air, but it can be water. If you've ever been in a swimming pool underwater, you hear sounds very distinctly under there, okay? Sometimes more clearly than you do above, okay? I think I've mentioned the old Cowboy in India movies or Cowboy and Bad Guy movies where they're checking to see if the train's on the way because they can rob the train or disrupt the train or something like that. They put their ear down on the track. And putting their ear on the track, they're going to hear the train way further away than they could listening through air. Because metal, solids, conduct sound quite well. That can be a medium. So air, water, solid, anything can be a medium. Then you have to have something to receive the sound. Okay? For us, it's our ears. Okay? And they are incredible devices. Absolutely amazing. I'm more amazed by them all the time now that I'm losing hearing in both of mine. But they're just incredible devices to be able to pick up all the nuances of sound. And then when you consider the frequency range over which the human ear responds is approximately 20 hertz, which is very low frequency, up to 20,000 hertz, okay? That's 1,000, 10 to the third, 3 orders of magnitude range for the human ear. That's pretty incredible, okay? Now, ultrasonic waves have a frequency higher than 20,000 hertz. And I'm guessing most of you, that's what you'll be working with, right? Ultrasound. You won't hear it necessarily unless you have some devices that bring it down to a frequency you can hear. But I've had ultrasounds done on me. I had a doctor once young doctor, he seemed like he panicked on everything. And he had detected just a trace amount of blood in urinalysis test that he did. And he was convinced I had bladder cancer. So therefore I needed to go have an ultrasound to detect where the cancer was, you know. So went and had the ultrasound. And it was sort of fortunate this happened because I had nothing wrong with my bladder. They said, fantastic looking bladder and that kind of stuff. But she just kept moving the device around, spreading some more gook on and stuff, and said, let me go get somebody. I said, was something wrong? She said, well, no, I see a shadow of something up on your right kidney. And I can't tell what it is. It may just be something intestinal or something, but let me go get my supervisor. So he came in, and they and at it a lot, and said, it looks like there is something there, but we can't tell what it is. We're going to need something else. So later they did not them, but the next group did, I think it was a CAT scan with and without contrast. And that time they found out I had a angiomyolipoma. Y'all know what that is? Angio is blood, myo is muscle, and lipids are fatty tissue. And I had just tons of them, little bitty things, in around my kidneys, not seeming to do anything, except one that was about 4 centimeters big. And they said, that thing's big and it may be growing, so therefore we need to get it out. So it was sort of fortunate I had a panicky doctor. By this time I was seeing a urologist, and so after a while I said, oh, by the way, do you detect the trace amount? It's microturia or something like that, meaning trace microscopic amount of blood in the urine. He said, oh yeah, well, I don't worry about that. He was a specialist urologist. He didn't worry at all, but that guy did. But because of that, they discovered that, and the rest is history. Okay. Wound up having half a kidney removed, but that was all right too. So sound refers to the waves transmitted through a medium with frequencies capable of being detected by the human ear. Or, for you guys, ultrasound, which you'll detect with devices. Okay. I won't read much of the rest of this, but sound waves are seismic waves that are transmitted through the earth, are detected using a seismograph. We just talked about those in my physical science class today. Moving on from there, musical instruments, everything, I mean lots of things produce and deal with sound. Now, light travels at incredibly fast speeds. We think of light as being instantaneous. It's not. It has a certain speed. The speed of light, let me get my pen set up. Okay. By the way, it's given the symbol c. Everybody understands that's the speed of light. This is 3.00 times 10 to the 8th meters per second. Okay? Subtract 3 from the 8 and you get 3.00 times 10 to the 5th kilometers per second. Well, a kilometer is about 0.6 of a mile, so do 0.6 times 300,000 and you get 186,000 miles per second speed of light. Incredibly fast. I'll write that down just so 186,000 miles per second. Okay? Just to give you a little perspective, you know the equator that goes around the earth? A light ray would travel about 3.5 or 4 times around the earth in a second. Okay? That is fast. I mean, that's flying. Okay? The speed of sound in dry air at 1 atmosphere of pressure, 0 degrees Celsius, which is pretty cold. So the speed of sound is approximately 331 meters per second. Okay, notice a difference there. That's 300 million meters per second as opposed to 331 meters per second. Incredibly slow compared to the speed of light. Speed of light is electromagnetic radiation, which travels at the speed of light. Speed of sound is a compression wave that has to bump particles into particles into particles, and that's what moves it. Much, much, much slower. Now, another little detail here. The speed of sound increases with the temperature at the rate of about, increases at a rate of 0.61 meters per second per degree Celsius. Okay? Now this was at 0 degrees Celsius. That's the freezing point. Right now, I would say we're pretty close to 20 degrees Celsius. Okay? That's about 68 degrees room temperature. Feels a little warmer than that to me in here. But let's just use 20 as a round number. So multiply this by 20, and you get 0 to 12. That adds another 12.2 meters per second. So we would be about 331 plus 12.2, something around 343 meters per second. I can't add. It's a 2, not a 3. Okay, approximately. Okay, it would be approximately the speed of sound in air at our temperature. Okay. Now, changes in humidity, temperature, also cause variation in the speed of sound. So dry air, like I've just given, here is the formula for it. I worked it out for you, but here's what it is. The velocity of speed of sound, whatever situation you have, in dry air, 331 meters per second plus 0.61 meters per second per degree Celsius times degree Celsius. Okay? Celsius temperature. That's what I just did down there. Add to 331, that. Now, what if you were measuring this in feet per second? U.S. customary. Velocity here is 1087. That would be feet per second. Okay. By the way, just as a quick check on this, there are a little over 3 feet in a meter, right? So if you multiply the 331 by a little bit more than 3, you're going to get something pretty close to 1087. That's where that comes from. That's feet per second. I'm sorry, they don't put parentheses around that one. Trying to set it up just like the book does. Okay. Plus 1.1 feet per second per degree Fahrenheit. Okay, not degrees Celsius. And then multiply that by how many degrees Fahrenheit. Okay. Oh, I'm sorry. Degrees Fahrenheit minus 32. Because 32 is the freezing point in Fahrenheit, and 0 is the freezing point in Celsius, so you subtract 0 from that and you don't have anything. Subtract this. So it's how many degrees above freezing you are. Okay. Now, any questions on those formulas, how you use them? Okay. So we need to go to example 1, and I've taken up most of the space on the slide, so I'm going to have to go to a clean slide here. But hopefully you got that down. I saw most of you writing. Find the speed of sound in dry air. Now they keep mentioning in dry air. Guess what? Here in Alabama, now maybe inside here the air is relatively dry because we're in air conditioning, and air conditioning does take a fair amount of the humidity out of the air. Step outside, there's plenty of humidity in the air, just about always in the southeast. So ours may vary slightly. It's not going to be a huge change, but they keep saying dry air, and that's why. At 1 atmosphere of pressure, and that's pretty common, we've got 1 atmosphere above us, so our pressure is very close to that, especially here in Birmingham. I do a lab with my physical science class that one of the first things we do is find out what the barometric pressure is. Now, I always assumed that because we're at a slight elevation above sea level, it's going to be a little bit less than 1 atmosphere of pressure, and weather conditions could change it more. We're just about always right at or very close to 1 atmosphere of pressure. And I found out later, also in my physical science class, that we're at a place where the heat rises on the equator and comes down around 30 degrees latitude, north and south. Guess where we're sitting? 33 degrees latitude. So we're under typically a little bit higher pressure than many of the bands north or south of us would be. So that's why we're right around, even though we're at a slight elevation, we don't sense it. Okay. So, example 1, find the speed of sound in dry air at 1 atmosphere of pressure if the temperature is 23 degrees Celsius, which is probably fairly much closer to what we have in here today. Okay, so what would be the formula? V is equal to, we're dealing with degrees Celsius, so we'll probably deal with the speed in meters per second. What is it in meters per second? 331 meters per second. That's at the freezing point at 0 degrees Celsius. Plus, and how much does it change for every degree? 0.61. That's about 2/3 of a degree of a meter per second per degree Celsius. Meter per second per degree Celsius times, and they say we're at 23 degrees Celsius. Okay? That would be a little bit more than what normally is room temperature. In fact, let me think. If 20 degrees is 68 degrees Fahrenheit, 23 would be about 73 or so degrees Fahrenheit. So that's about probably what we are in here. Okay? What would be the new velocity? Speed of sound in air at that temperature. 331 meters per second plus, now someone with a calculator, 0.61 times 23. Second? 14.0? Okay. And that, see, the degrees Celsius cancel out, and that would also be meters per second. Add those two together, and you get 345 meters per second. Okay? So it changes a little bit. 345 meters per second. Now, any questions on that? Example 2. What is the time required for the sound from an explosion to reach an observer 1,900 meters away from the conditions in example 1? Okay, so this is the speed of sound under those conditions. What time is required for the sound from the explosion to reach the observer 1,900 miles away? And that's 4 significant digits, by the way, for the conditions of example 1. Well, I don't know if you remember, assuming we did it, but let me give you a formula here. Distance, now, what you want to use as your symbol for distance? I kind of like D, but you could use X, you could use S, you could use just about anything you want to. What would you like to use for distance? Anything? Give me a letter that makes sense. Not V, not T. Give me a letter, any letter. Second? S? Is that what you said, or X? S. Okay. S is equal to, that's distance is equal to velocity times time. Okay? Does that make sense? If you're traveling at 60 miles per hour and travel for 2 hours, how far do you go? 120 miles, right? Same thing here. So in this case, our S is this distance 1,900 meters away. Okay? Our velocity is 345. So this will be at 345 meters per second. What we'll ask for, what is the time? What is the time for that to reach? Okay. Two ways you can approach this problem. Either solve that equation I have there for time and then plug in the numbers, or plug in the numbers and then solve for time. I call it chug and plug or plug and chug. I don't care which one you do it. Which you want to do, plug in first or solve for t first? Second? Plug in first, okay? So it'll be 1900 meters is equal to 300, that's an ugly 3, isn't it? 345 meters per second times t. We're looking for t. What is the time? That's the question. So how do we find the time? Divide both sides by 345 meters per second. Divide this side by 345 meters per second. Now notice here that 345 goes out, meters per second goes out. Everything's gone there except t, so that's what's left there. That's what we're looking for. Okay? And then 1900 divided by 345, what does that give us? 5.51. And what unit would that be? Here the meters cancel out, and you're left with 1 over second, which is the same as 1 times second over 1. So that would be seconds. So it takes about 5.5 seconds for the sound to reach you. Okay, name please? Katisha? Okay. Good deal. All right. Good deal. We're kind of filling up now. This is good. Still missing a few. Let me say this again because I said it earlier before you came in, so just in case you don't go back and listen to the first part of the class on YouTube. I have passed out to everyone test 1. I've got most of them back, but not all. I think I'm missing 2 maybe. And I've passed out all of to everybody test 2, and I think I've got all but 3 back on test 2. And I passed out to everybody test 3. I hope I have. Do you have test 3?
I didn't get test 3.
Okay. You need test 3? Okay, that's why I'm saying this, trying to make sure everybody has everything. And that's test 2?
Mm-hmm.
Good deal. Okay, let me find test 3. Yep, that's test 4. That's, I think, test 2. That's it. Okay, now hold on just a second. Question number 3, they had a misprint. They said the vertical steel columns of an office building each support a weight of 50,000. That doesn't make any sense. It's 50,000. That's 50,000 pounds. And then the same in the B part of the question, what would the compression be if the weight were 60,000 pounds? So just put an extra 0 on both of those. I think the rest of them are okay. This is a lousy test bank in this book. Pretty good book, but a lousy test bank. Okay. All right. We just finished doing example 2 on page 437, and they got 5.51 seconds too. Now, where do you notice that the speed of sound is much slower than the speed of light? Have you ever noticed that? I bet you've noticed this. I bet you've seen lightning flash out there, and then it's several seconds before you hear thunder, right? That thunder happened at the same time as the lightning, but it was so far away, lightning you saw almost immediately, sound took a while to get here. You probably, I'm guessing, have watched an airplane fly over. And you see the airplane here, but it sounds like it's back here. That's because the sound from when it was there is just reaching your ear when it's really over here. So you probably have had both of those experiences, but at least the lightning and thunder. All right, any questions on this before I lose the slide? Okay. That's not what I want. Okay. This is what I want. I really don't want to, but I've got to. In order to go back and forth, I have to close one out and pick up the other one. Okay. Let's go from current slide. All right. Now, sound propagates faster in a denser medium, okay, than it does in a less dense medium, okay, such as air. The list of the speed of sound in various media is given in this table here. Oh, man. Old and sore. Aluminum, much denser than air. It has a speed of 6,420 meters per second, as opposed to air, 331. Okay, quite a bit of difference there. Feet per second, what was it, 1,000 for air, 21,000 for aluminum. Brass, I would have thought brass was denser than aluminum, but I don't think it matters as much within this. 4,700 and 15,000 feet per second. The steel, and no steel is denser than aluminum, so the density doesn't matter in these things that are in the solids as much as it does between solids and gases. So that's almost 6,000. This is 19,500 feet per second. Granite, this is rock, 6,000 as opposed to 19,700 feet per second here. 6,000 is meters per second. Alcohol, okay, a liquid, still faster than air by a significant amount, 4 times almost as fast. Same thing here, not quite 4 times as fast. Water, more than 4,000, almost 5 times as fast. Dry air, again, 331 to 1090. Vacuum, zilch, 0, not at all. Okay? So, outer space, no sound waves. None. There's nothing to bounce off of. So, there's a little blurb here on the next page. This is page 438 on a fairly well-known American inventor, Alexander Graham Bell. Okay? Actually born in Scotland, he invented the telephone, the telegraph, and established Bell Telephone Company in 1877. So I said he was American. He's really more Scottish. Okay? There's several ways that we talk about sound, characteristics of sound. Okay? We say a siren is loud. Okay? Or maybe the teacher is loud. Okay, that may be true too. Whisper is soft. Okay, you can hardly hear that, right? Music could be loud or soft. Okay, good or bad. Okay, physical properties differ from those sounds. For these sounds are intensity and frequency, 2 of the characteristics that we deal with. Intensity is that loudness thing. Okay, I'm hard of hearing, so I'm pretty sure that's why I'm a bit louder than I should be, because I don't hear it that well. Okay. You probably say, yeah, we hear it fine. Okay. Frequency, quite often, especially if you're a singer, you talk about pitch. Those are very closely related. Okay. So let's hit the terms here. We'll come up on this in just a second, and I really hate to lose this slide, so since Deidre's not here, sorry about that, Deidre, let me put the definitions over here. And every time I change, I have to go back and get my pen back. All right, here we go. So, intensity. That is basically loudness or softness. The energy transferred by sound per unit length of time through the unit media, a unit area, and therefore is power over time. So intensity is power over time. Now, does anyone remember a unit for power that we used? And let me tell you not to use this one. Horsepower makes no sense when you talk about sound. So that's not the unit of power to use. Okay? What other unit of power did we use back in chapter 8 maybe? Named after James, another Scott. What? Yeah, watt. Okay. So this would be watts per second. That would be, watts per unit area. Watt. So I wrote it down wrong. Sound per unit time through a unit area. Okay. Okay. Watt per, okay, sorry. Let me clean this up some, okay. I was reading one thing. It's energy per unit time per unit area. But energy per unit time, that is power, okay? So that incorporates the time, and this is per unit area then, okay? So it's watts per meter squared. If I can get my pen back. There we go. Per area, and that's watts per meter squared. Now, a square meter is a big area, so this is probably going to be a fair amount of power. Okay. Loudness refers to the strength of the sensation of sound heard by the observer and describes how strong or faint the sensation of sound seems. The ear does not respond equally to all frequencies. Sound must reach a certain frequency before it can be heard. The human ear normally detects sound ranging from intensity of 10 to the minus 12 watts per meter squared. That is an incredibly low number, okay? That's the threshold for hearing, up to 1 watt per meter squared, okay? That's the threshold for pain, okay? So the threshold for hearing, so let's go to the next slide, and you'll see that those data being presented here. Oh, man. All right, threshold for hearing, 10 to the minus 12 watts per meter squared. That's scarcely audible. I guarantee you I can't hear that, okay? My hearing is so bad, I'm considerably above that. Now, there's several things that go on when you age. One is that you don't hear as well, but secondly, you don't hear frequency range as well. Now, this was discovered, I think it was either in Canada or Britain. I mean, it wasn't discovered, but kind of was, by some high school students in either Canada or Britain, somewhere like that. They realized that because most of their teachers were older, they weren't able to hear as high frequencies as the students did. So what the students did, they put their ringtones at a very high frequency so that they could chat with each other, or text each other, or whatever with their cell phones, and the teacher would never hear it go off, okay, because it was at a very high frequency. Until they had a very young instructor or teacher who happened to have exceptionally good hearing, and he or she, I don't remember which it was, heard it, and he confiscated the phones. They found out what they were doing, found out all the other teachers had been duped, thinking the students were taking good notes, whereas they were really texting their friends. Okay, not that any students I know would do something like that. It must have been somewhere else. Okay, minimal sounds, and by the way, here's another unit that's mentioned here, and they have done a really lousy job of introducing it. They do mention it here. Levels of intensity are also measured on a logarithmic scale. That's decibels, whereas a bell is named after Alexander Graham Bell. That's why they mention him. And what do we mean by a logarithmic scale? Does anyone know? Okay. What a logarithm does is basically converts a huge range of numbers into a very usable range. And it does that by basically powers. Okay? Now, I can't remember the context I was just giving. But let's say that whisper we were talking about, that is basically 10 to the minus 11. The threshold for music scarcely audible is 10 to the minus 12 watts per meter. 10 times this amount makes it 10 to the minus 11. Well, on a decimal, on a log scale, that's an increase of 1. Not a power of 10, 1. Every power of 10 results in a different digit. So here we're talking about 10 units becoming 1 unit. Okay? So, oh, that's not quite true. I'm sorry. So a very small number like this, 10 to the minus 12, it becomes 0. 10 to the minus 11 becomes 10. 10 to the minus 10 becomes 20. So you see, this is a power of 10 here, and yet it's a difference of 10 there. Not a power of 10, a difference of 10. Okay? So for every power that it goes down here, factor of 10, it goes up 10 units, and that's all. Okay? These numbers, believe it or not, are getting larger. The exponents are getting smaller. This is a power of 10. This is a 10 units. Okay? And you go up to deafening and painful. That would be right around here, 120 decibels. You should not ever allow your ears to be exposed to that for very long. The 100 feet from a jet engine, you're at 130. You can have some pretty serious damage from that. Shotgun blast, 140 decibels. Really, really painful. Okay? So if you are ever firing a weapon, practicing shooting or whatever, wear sound suppressors. Never go in there with just your ears. Okay? If you're ever near an airport, that you're outside at the thing, those people, you'll notice, people that work at the airport, sound suppressors. Otherwise, they're going to be going deaf. If you're at a rock concert or a prop plane nearby that, that's about as high as you should, and you shouldn't expose yourself to that for very long. Okay? My older brother was talking just this weekend about the house he lived in Dublin, Georgia, sat well back off the road, probably further from here than to that building over there, at least that far, off the road. The house was reasonably well insulated. He was inside the house and listening to his turntable. This was many years ago when people still listened to radios on turntables. You know, the needle was playing along. And a car rode by, and literally he could feel it vibrating the house. Their radio was on so loud, and it made the needle jump a couple tracks on the record. It was that loud. And I said, those people will not be able to hear in 10, 15 years, hardly would at all. He said, I don't think they could hear then. If they had it that loud, they had to be high. So that's what a decibel is. It's a log scale that takes a huge range of numbers, 10 to the minus 12 to 10 to the 2. That, by the way, is a factor of 10 to the 14. That would be 1, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma. It's a huge number. That would be 4 sets of 3 zeros with 2 more zeros up here with the 1. 100, that's more than trillion, 100 trillion times between this and that, and it's 140 difference here. So it's quite, a log scale really condenses it down to much more usable numbers. You probably should stay in the 60, 80 range is the safest thing to be, I think. Lawnmowers, things like that, motorcycles, that can be harmful for too long. Hair dryers, diesel trucks, chainsaws. I feel really bad when I read this list because I grew up on a farm. Tractors, chainsaws. We didn't often shoot, but every now and then, firing at a snake or something like that. Of course, that kind of stuff. But I was exposed to way too much noise, and that's probably part of the reason I don't hear well now. Okay. Now, most of you are in medical field, so you've probably seen illustrations like this, but before we go there, let's talk a little bit of the pitch of a sound. Is the effect the frequency of the sound on the ear. Higher pitched sounds have higher frequencies than lower ones. Okay? If I were talking a sound like this, that's a very high pitch, and this would be a very low pitch. Nothing to do with intensity, it's just the frequency of the sound, the pitch of the sound. Okay? And that depends on how many vibrations per second. When I talk real low, I've got the vocal cords so they're not producing that many vibrations per second, whereas really high pitch, I'm forcing the larynx to go together so it's more vibrations per second. Okay, now let's look at the ear, and let's not go into too much here. But number one, the shape of the ear is just like those old megaphone in reverse. It captures more sound, and all those little grooves and things sort of funnel it into the ear. Okay? Here's the external auditory canal, and I noticed this when I was in the Navy, my ear canal is much bigger than most people's, I think, because they gave me, I was on an aircraft carrier. Okay, go back here for one slide. Jet plane, jet engines. My bunk on the aircraft carrier was just below the flight deck, just aft of the jet blast deflector hydraulic room. Okay? And when we were launching at night and I was supposed to be sleeping, the only way you could try it was to have earplugs in your ear. Those earplugs would fall out. I'd push them in, I'd get them in as tight as I could, go to sleep. The next morning I'd wake up and they'd be on the pillow somewhere. They just would come out overnight, okay? Because my ear canal, because I was already hard of hearing, and my body had adjusted to that by having a bigger ear canal, okay? So, and by the way, what an aircraft carrier does, those jets are revved up as fast and hard as they can be. Now, you have people on the flight deck, that jet blast that would come out of that would fry them to toast immediately. So they have these jet blast deflectors. They're part of the deck. It goes up. There's hydraulics that lift them up and raise them to about 45-degree angle. Then the jet turns on his blast, and it's deflected straight up, not out onto the deck. Now, that jet exhaust is blue. Hot. Hotter than a red flame, hotter than a yellow flame, a blue flame, the very hottest. Have you noticed gas ranges? Blue flames. Extraordinarily hot. If that were just metal, it would be melting the metal. So they actually pump water, seawater, through that jet blast deflector constantly to take off the heat to keep from melting the metal. So these are heavy, heavy chunks of metal with water going through them. And they raise them up, and the hydraulic get them up to this angle, and then the jets, and that's just above my head. through a metal deck, which transmits sound really well. And then, when the jet takes off, I feel a thump because the catapult that throws it off the end of the aircraft carrier, hits the end, and you feel a thump, and then they pull that back, coming back, and then the jet blast deflector, boom, all night long, okay, or whenever they're doing flight ops. And they did, on an aircraft carrier, they measure your hearing coming in. Mine was really borderline. It was just in the normal range, but just barely. When I left 1 year later, it was below normal. So I should have gotten something immediately from the VA or Navy or somebody, but I didn't bother to do it because I thought it wasn't going to get any worse once I wasn't in that environment. It did. And now I don't qualify. So, too bad. But that's your ear canal. Then here's the eardrum, called the tympanic membrane. We call it the eardrum, or most of us do. And this is the outer ear, or the external ear. The middle ear has these things, and in the old days, they called this the handle and the stirrup, okay? The proper names are the malleus, which sounds like a mallet or a hammer, and the incus. I don't know what that sounds like, but those are the two parts of the middle ear, okay? And then this transmits the sound through this bone. I think it's mostly bone here, to the, and this is called the stapes in the oval window, okay? Strange name, but I think we used to call it the stirrup, okay? So that's what it looks like. And then the inner ear, the vestibule, hopefully you know about this, the semicircular canals, which are these things, and then the cochlea, okay, is like this. It looks like a seashell type thing. By the way, here's a round window, they call it, and this is the eustachian tube. Any of you ever heard of that? Have you ever sensed the use of that? Have you ever taken plane flights or driven up in the mountains and your ears pop? That's because the eustachian tube is supposed to equalize the pressure. See, everything here is sort of internal. If you go someplace like up in a plane and the pressure drops, then your eardrum is going to be like it popping out because the inner pressure is greater than the outer pressure. The same thing can happen when you're coming down too, then the outer pressure is greater than the inner pressure. The eustachian tube goes to the back of your throat somewhere, and that's supposed to help equalize the pressure. So they say if your ears are clogging up, hold your nose up, or chew gum, or do something to activate and open up the eustachian tube. Now, quite often young kids, very young children, if they get a cold or something, theirs are so small to begin with, if they have any swelling of the mucous membranes, then that can stop up, and then their ears give them fits because that's tiny little eardrum, tiny everythings, and the little bit of pressure difference can make a world of difference, and they will scream bloody murder for that. Now, what's this? These are the nerves. These are actually electrical conductors that carry the signal that these things pick up and carry it to the brain. The brain interprets, and that's how you hear it. All that's going on instantaneously, by the way, without you even thinking about it. Okay. Next section, okay, the Doppler effect. Refers to a variation in frequency heard when the source of sound, now remember sound travels slowly, right? So what if, I don't think I can do this to make it make any sense, but if I were emitting a constant sound, constant frequency, and I came running to you, then the sound that I was emitting, which normally would be constant frequency and pressing the air. If I was running to you, then the air is getting pressed not just from the sound, but also from my moving to you, so it presses things closer together. Well, closer together means shorter wavelength. Shorter wavelength means higher frequency. Okay? Or if I was running away from you, emitting that same sound, then longer wavelength, lower frequency. Okay? That's the Doppler effect. Christian Johann Doppler, Austrian physicist and mathematician, best known for his explanation of the perceived frequency variation in sound and light waves, by the way. Even though light travels so incredibly fast over long distances, you still get what they call a redshift. Now, why a redshift? Red is the longest wavelength of visible light, and if an object is moving away from you, its light is shifted to the red length. And that's what a guy named Hubble discovered, that galaxies experience redshifts, that actually galaxies are moving away from each other enough so you can tell the difference in the light. Doppler effect, same type thing. Okay. Now, here is the formula that we use for Doppler effect. And again, I'm going to stay on this page just a little bit longer. Oops, wrong way. Goodness, I don't have much room to write anywhere. Okay, let me write here. Here's your formula for the apparent Doppler shifted frequency. And by the way, has any of you heard Doppler used in any other context? What? Weather. Those are Doppler radars. What does that measure? It measures a compression wave coming to or going from, and if it's coming to, then it's shifted higher frequency. Going away is shifted a lower frequency. If they represent those frequency with color, maybe green coming to you, red going away, or vice versa, guess what? If you see the color change quickly, that means spinning motion, tornadic activity. That's exactly what a Doppler radar is telling you. It shows you where frequency is changing rapidly from increasing to decreasing, and that indicates spinning, tornadic activity. And they use that a lot. Jerry Tracy, okay. James Spann. I can't think of the others' names. Okay. Now, here is the Doppler, apparent Doppler shifted frequency. Okay. Now, frequency is F. So F prime is the Doppler shifted frequency. Okay. That's what it sounds like. It's equal to the frequency, the actual frequency being emitted by the source, the siren, the, whatever it is, okay? And by the way, what is radar? Radar is waves going towards something and then bouncing off and coming back, okay? Radar is used to measure, in the Navy we used to use it to detect ships when they were far away from us, to give the range, and you could calculate the speed of the ship and all sorts of stuff just by knowing that radar. They do it with aircraft. The control towers, they've got radar going all over the place. That's what a radar is doing. It's a radio. Radar stands for something, but it's a shift. So that's what you're measuring is frequency. And here's what we've got. Multiply that by the ratio of V, which is speed of sound in the conditions that you happen to be, divided by the speed of sound plus or minus the speed of the object. And I'm going to call that S for source. Whatever is emitting that sound. Okay? Now, why the plus or minus sign? Now, these feel a little backwards, and it's because they're in the denominators. The plus sign in the denominator is used when the source is moving away from you. So in that sense, if it's moving away from you, use a plus sign, because when your denominator gets bigger, your frequency gets smaller, right? 1/3 is less than 1/2. Bigger number in the denominator meaning a smaller distance, okay? I did say that right. 1/3 is less than 1/2. I don't know which way I said. Okay. So the minus sign is when the sound is coming to you, okay? And that's your, that's one formula with a plus or minus sign goes both ways. All right? Now, here is what I was just trying to describe to you, me walking or running to you while I was making a uniform sound. Here's a car. Moving to the left, observer A is the guy standing there in front of the car, dumb place to stand. Here's the car horn. Why? Because you're standing in front of me at a higher pitch than the driver, because the driver's in the car. Observer B is back there, and because the car is going away from her, she hears it at a lower pitch. Okay? So, the driver in the car hears the horn exactly as it's pulsing. Okay? This guy, the sound waves are being bunched up, so the frequency is higher. Okay? This gal over here, because the sound waves are further apart, the frequency is lower. Okay? Have you ever been at a railroad crossing? Okay? And the train is coming to you, blowing this horn like crazy. Same thing will happen with a fire truck sounding its siren, a police car sounding its siren, an ambulance is sounding its siren. If they're coming toward you, now sure, they're getting louder because they're coming closer to you, but they're also going up in frequency. Okay? The pitch is going up. But then when they pass you and go away from you, the frequency drops. Yeah, they get softer because they're going away, but the frequency goes down. So you hear that, you know, it's a frequency thing as well as a loudness thing. So let's do example 1. Okay? And I don't have any room to do example 1, so this time I will get out, sorry about this, and get back in to this one. Okay, and I've got to change my color back again. Okay. An automobile sounds its horn while passing an observer at 20 meters per second. So the automobile, okay, the V sub A is equal to 25 meters per second. That's the velocity of the automobile. In our formula there, that was your source. So let's call that V sub S. V sub S, 25 meters per second. The actual horn frequency, so this is F in our formula that we had, was 400 hertz. 400 with that significant digit, hertz. That's the frequency. Assume that the speed of sound is, so here's your V, not the Vs, but your V, speed of sound is 345 meters per second. What was that? Around 72, 73 degrees? Seems like that was it. Okay? The A part of the question here. What is the frequency heard by the observer while the car was approaching? So what was the frequency that he thought he heard or she thought she heard? What was that formula? Okay, is equal to the, right? V over. Okay, and which do you use if the car is approaching? minus, okay, Vs. The reason for that, it makes the denominator smaller, which makes the frequency larger, okay? So remember it that way. So this is what we're looking for, V prime. The actual frequency was this V, 400 hertz, times the velocity of the sound was 345 meters per second, divided by 345 meters per second, minus the speed of the source, which was 25 meters per second. Okay? That would be 400 hertz times 345 meters per second divided by 320 meters per second. Whoops. Okay. Yeah. So if someone's got a calculator, punch away. See what you get. Notice the meters per second cancel out and you wind up with hertz. Now, I could almost do that in my head if I divide 40 into 320. So get rid of the 0. That would be 10 over 8, which is 4 over 5 over 4. And, well, I'll let you do it. If you want to do easier numbers, 5 times 345 divided by 4. Anyone got a calculator? 431. Let's just leave it 0.25. 431 hertz, approximately, because we only had 3 digits coming in. Actually, that 25 is only 2 digits, but we're going to let us get away with that. So 431 hertz. Very good. All right. Now, the B part said what was the frequency heard while the car is leaving. So the B part, what will be different about that? Your F prime, yes. Everything else will be exactly the same. F times V over V plus Vs. Okay? So that will be 400 hertz times 345 meters per second over 345 meters per second plus 25 meters per second. And that will be 400 hertz times 345 meters per second over, when you add those two together, you get 370, I believe, right? Meters per second. Meters per second cancel out, and somebody do the math for me. See, this will produce a smaller number than before. The frequency is going down as it leaves. 373 hertz. That sounds like about what they got. Yes, it is. Good for you. Good for them. All right. All right. There's a physics connection here on ultrasound. So if I were you, this would definitely be something that I would want to read. Okay? And what I've always worried about, though I'm sure they must have done plenty of tests for these people who keep wanting to have ultrasounds of that baby, I hope that's not bothering their ears any. I know it's higher frequency, but, I just think, do we need to be pumping all that energy in there? So I don't know. Problem set 16.4, you can do any of the odds. I think the odds have answers in the back. I said any through 1 through 5, but you can do 1 through 19. Okay. And let's see. 16.5 is resonance. I guess we need to do a little bit. There's hardly any problems left. Just one more example to do in the next 2 sections. So I think we can hit this. I see people beginning to pack up. So I guess we're getting sort of short. Sorry I was so late getting here with the traffic and everything. So we'll start next time in 16.5, resonance, and 16.6 is simple harmonic motion. There is one problem with that. Now, most of what your test is on the stuff we've covered so far through 16.4. Do you want to go on and take that and get started on it? You don't have to, but if you want to, you can. And that way you get an extra little bit of time to work on it. Okay. Okay, here we go. And I do have a correction or two to make on it, so don't leave until I've made these corrections. I got them corrected on some of them, but didn't have them done on all of them. So hold on just a moment until I can do it. So make sure, even if you have it on the paper, make sure you can read my ugly writing. It's not that funny. Okay. All right. The first several questions are very straightforward. I think you won't have any problem with that. Oh, wait, I'm sorry. Number 10 is based on that last section, which we haven't done. So don't bother with 10 if you don't want to. Okay? But number 8, and whoever proofed this, I mean, I can't believe this is 11th edition, and they still have this many errors in the test bank. Number 8, a train traveling at a speed of 80 miles per hour approaches an observer at a station and sounds a whistle. At what frequency? They didn't tell you. So here's a whistle at 585 hertz. So that goes right there at the whistle. Sounds a 585 hertz whistles. However, the whistle of 585 hertz. What frequency will be heard by the observer? Okay? Because the train is approaching the observer. Assume the sound velocity in the air is 1090 feet per second. Now, one thing I hope you notice right there. Anyone notice anything? When I ask a question like that, a good place to look would be the units. What do you notice about units? They're different. So you're going to need to convert, I would suggest, the 80 miles per hour to so many feet per second. Okay? And then do your problem. Because you cannot do that problem. Notice here, one on the board, V over V plus, notice how the meters per second canceled out? If you had one of those in miles per hour and the other in meters per, and feet per second, you're not going to get anything to cancel out.
So you should convert it to lit?
Convert the miles per hour to feet per second. We've done that many times, and y'all enjoy doing it every time, if I recall. Yes, I thought so. Okay. Now, number 9. A car is traveling away from you at 70 miles per hour. The car horn produces a sound at a frequency of nothing. They set it up, but never gave the frequency. What frequency do you hear? Well, you need a frequency there, don't you? That frequency for the car horn is 5,000 hertz. 5000 hertz. And since the only other thing that's mentioned there is miles per hour, and you got 3 digits there, put the bar over the middle 0. 500 bar 0. Okay. Put it over the middle 0. Okay. Now, it didn't say anything about the speed of sound in air, so use the same speed you used in the previous one, because it's the same type problem. So use 1090 feet per second. Don't worry with number 10. We'll do 10 next time we'll do something like 10 next time so you can do that. So get done what you can, 1 through 9. But you don't have to do any of it if you don't want to, because the time clock on this won't start running until we finish the chapter, which will be next time. And that will be Thursday, by the way, right? See you all in 2 days. I sure hope so. Any questions? Good deal. Thanks for being here. This is my best attended class of the day. My morning class, 0 for 7. My second class, about 5 for 7, so y'all are right up there. Yes. Okay. Which test?
12, chapter 12.
The which?
Chapter 12.
Okay. All right. You want me to get a new clean screen here?
Yes.
Okay. I'll record this for everybody then. Don't know if they're going to pay any attention. So, chapter 12 test. That was test 2 or test 3? 3. Is that the one that starts, find the work done? Or no, a force-off. Yeah, that's the one that starts a force-off. Okay? Oh, let me read this open. Okay. Was there a question? Which one? Huh? Number 3. Okay. Chapter 12, right? And this is pretty early in chapter 12. Okay. All right. On page 316. Doesn't that look like an appropriate formula? Wait, may not be. Let me see. No, maybe not quite. No, yeah, I'm sorry. Hooke's law is what I was looking for. Sorry. I didn't read the whole problem. This is Hooke's law on page 321. Right? Is that what you were using? Yeah. Hooke's law of 321.
I have a question on that. Like, would it be like the example, like an example 2 or example 3? I used the example 3. I guess it's still the same thing, but I like soft or I used the one on 322 where it got where you saw off the one and then you plug in the next one, plug in to get part B up.
Yeah, you first figure out what K is. That's the A part of the question. What is the spring constant? That's a dead giveaway. It's Hooke's law. And then once you find that out, then plug in the new condition. Right. Does that make sense?
I guess the numbers just sound like, okay, I have one. For number 1.
Okay.
Did the force over the push formula?
Okay, that's also Hooke's law. Anytime you're stretching a spring. What's that?
You said that's Hooke's law too?
Yes. And one of the key words in there is similar. What force will stretch a similar spring? That means same spring constant. All right, good deal. Thank you. What's that?
I left my spreadsheet and paper while I worked my problem.
That's excellent. I really like to have those so I can see if I can figure out where you made your error, then maybe I can give more partial credit. Wow, that's all you needed, huh? Oh, you have another?
I guess.
All right, good deal. Thanks. What's that? I can't hear you.
Can go ahead and grade it like that.
Okay,
I
let
don't
me.
think I did the first one right. I know I did.
Okay. All right, let me.
Yeah, put 2 S's. I don't know.
Okay.
This test was a little harder than.
Okay. If we're through with the
Yeah.
questions, then let me